Most of the daily routine work is done by electric motors, and the forces behind this work are the magnetic forces, and we already studied them in the previous lecture. So now today let's discuss the simple case where which is a case of a simple motor consisting of a single current carrying loop, and it is placed in a magnetic field. And in this one, two magnetic forces, positive and negative F produce a torque on the loop. And this loop, because of these two forces, rotate about its central axis. But there are various phenomena which we can study here, which are the cause of the rotation of this loop. So let's do the quantitative analysis here. A rectangular, consider this a rectangular loop of side A and B, and a current I is flowing through the loop, and this is in a uniform magnetic field. So we place the loop in the field in such a way that its long sides are perpendicular to the field direction. This one and we label them 1 and 3, and the short sides are labeled 2 and 4 are parallel to the field directions. So here the field is into the page, and this is a more simplified figure of this loop. The side S1 and S3 have forces F1 and F3, S2 and S4 have forces F2 and F4, and S2 has length A, S1 has length, S2 has length B, S1 has length A. So to define the orientation of the loop in the magnetic field, we use a normal vector n that is perpendicular to the plane of the loop, which is shown here, this one. And you can find out the direction of the n with the help of right hand rule. Just curl the fingers of your right hand in the direction of the current at any point in the loop, and your extending thumb points the direction of the normal vector. Then the normal vector of the loop is shown some arbitrary angle here, theta, to the direction of the magnetic field B, some theta, and so we are interested to find out the net force and the net torque. So to find the net force on the loop is the vector sum of the forces acting on its four sides. For side 2, the vector L points in the direction of the current and has magnitude B. The angle between L and B for side 2 is 90 minus theta. So the magnitude of the force acting on this side would be, we know, F is equal to ILB. So from there, from that equation, IB, and the angle is sine 90 minus theta, which is equal to cos theta. So IBB cos theta. And the force F4 acting on side 4 has the same magnitude as F2 but the opposite direction. So F2 and F4 cancel out, their net force is 0, and because their line of action is through the center, their common line of action is through the center of the loop, and there will the net torque because of these two forces is 0. But the situation for the side S1 and S3 is different. For them, L is perpendicular to B. So the forces F1 and F3 have the magnitude F1, F3 have the magnitude IAB. These two forces have the opposite direction as well, but they do not tend to move the loop up or down. And these two forces do not share the same line of action. If they do not share the same line of action, they are able to produce a net torque. So the net torque, so this torque actually has a tendency to rotate the loop, and when this loop rotate, so it aligns its normal vector n with the direction of the magnetic field. So the torque for this one, the torque has moment arm B by 2 sine theta about the central axis of the loop, and the torque, the magnitude of the torque due to F1 and F2 would be I E V B by 2 sine theta plus I E B by 2 sine theta, and this becomes I A B sine theta. Now if we replace the single coil of current with a coil of n loops or turns, then, and we suppose that the turns are wound tightly enough so that they can be approximated as all having the same dimension and lying in a plane. Then the turns form a flat coil, and a torque with magnitude this one act on each of them, this one. Then the total torque on the coil has the magnitude, and we will multiply this one with the n turns. And we know AB is the area enclosed by the coil, so this would be NIA into B sine theta, and so NIA are all the properties of the coil: its number of turns, its area, and the current I it carries. And this equation holds for this one, holds for all flat coils, no matter what their shape, um, provided the magnetic field is uniform. And instead of focusing on the motion of the coil, it is simple to keep track of the vector n, which is normal to the plane of the coil. So one more concept which is also related to this is the magnetic moment or magnetic dipole moment. We know a torque acts to rotate a current carrying coil placed in a magnetic field, and in that case here the coil behaves like a bar magnet which is placed in the magnetic field. So like a bar magnet, a current carrying coil is said to be a magnetic dipole. So the torque on the coil due to the magnetic field so to account for the torque on a coil due to this magnetic field, we assign a magnetic dipole moment mu to the coil. The direction of mu is that of the normal vector n to the plane of the coil, and this is given by the same right hand rule. So you grasp the coil with fingers of your right hand in the direction of current I. The outstretched thumb of the hand gives the direction of n or the direction of dipole moment, magnetic dipole moment. The magnitude of the dipole moment is NIA. This is the magnetic moment, in which N is the number of turns in the coil, I is the current through the coil, and A is the area enclosed by each turn of the coil. So, this one. So, using this one, we can rewrite the equation of the torque on the coil due to a magnetic field. Torque is equal to mu B sine theta, in which theta is the angle between the vectors mu and B. So we can generalize this vector relation as this is it can remind you about the torque exerted by an electric field on an electric dipole, which was tau equal to dipole moment into E. So in each case, the torque due to the field, either magnetic or electric, is equal to the vector product of the corresponding dipole moment and the field vector. So a magnetic dipole is in an external magnetic field has an energy that depends on the dipole rotation in the field. So we can write that u theta is mu dot b. It is also in analogy with the electric dipole, where the energy was P dot E. So the energy due to the field is equal to the negative of the scalar product of the corresponding dipole moment and the field vector. A magnetic dipole has its lowest energy when the angle between the magnetic field and dipole moment is 0 or cos 0, or you can say when its dipole moment mu is lined up with the magnetic field. It has its highest energy when mu is directed opposite to the field. This one. And then the one more important point, the unit is of mu is joule per Tesla. Okay, if an applied force due to some external agent rotates a magnetic dipole from its an initial orientation theta I to an other orientation theta F, then work done on the dipole by that applied force or by the applied torque is given by F minus Ui. So we just write potential energy in the terms of work. If the dipole is stationary before and after the change in the orientation, then we can write this equation like this. And here UF and UI can be calculated easily. So so far now we have identified only a current carrying coil and a permanent magnet as a dipole. However, rotating sphere of charge is also a magnetic dipole. And most of the subatomic particles, including the electron, the proton, and the neutron, have also magnetic dipole moments. And all these quantities can be viewed as a current loop. So let's do one sample problem which is related to this concept, and then we will move to the next topic.